Hello and welcome. In this session, we'll have a look at modal orthogonality principle, which helps us in analyzing multi-degree of freedom systems using modal superposition method. Now, if I have mode shape vectors, I can create a mode shape matrix out of this. So it will have size n by n. Let's denote the mode shape matrix by capital Phi, comprising of each mode shape vector phi. Now if I have 3 degree of freedom system, I can write the mode shape matrix as capital Phi, which will be 3 by 3, wherein I have phi 1, phi 2 and phi 3, which is nothing but mode shape 1 at corresponding degrees of freedom, mode shape 2 at corresponding degrees of freedom, and mode shape 3 at corresponding degrees of freedom. Now this can be very well written in matrix notation as phi jn, where j is the degree of freedom and n is the mode number. For example, if I have phi 1 1, it is indicating mode shape at first degree of freedom in first mode. Phi 2 1 is indicating mode shape at second degree of freedom in first mode. Phi 3 1 is indicating mode shape at third degree of freedom in first mode. Now for ith mode, if I write using the characteristic eigenvalue equation, it is k phi I is equal to omega I square into mass matrix into phi I. Let's name this to be equation 1. Now for jth mode, k phi j is equal to omega j square into mass matrix into phi j, that is the mode shape in jth mode. Now we can pre-multiply equation 1 using phi j transpose and equation 2 by phi I transpose. Now if I pre-multiply with equation 1, I get equation 3. So if I am multiplying phi j transpose k phi I equal to phi j transpose into m into phi I, omega I square is a scalar quantity, so it doesn't get affected, so we are writing it in the beginning. Now if I multiply phi I transpose to equation 2, it will become phi I transpose into k phi j equal to, now omega j is a scalar quantity, so this is omega j square phi I transpose into m into phi j. Now we'll take transpose on both sides of equation 3, that is phi j transpose k phi I transpose of entire left hand side is equal to omega I square phi j transpose m into phi I transpose of this. Of course omega I square is a scalar quantity, comes out, so we have phi j transpose k phi I transpose of the entire thing equal to omega I square phi j transpose m into phi I transpose of this. Now from matrix we have few identities which we can use. So we have A transpose and transpose of that is nothing but matrix A, and AB transpose is nothing but B transpose A transpose, that is the order reverses. So in this case, if I am taking phi j transpose k phi I transpose of this, now what will happen, phi j transpose and transpose of phi j, it will become phi j, and here we are having product of two matrices and their transpose, so the order will reverse. So phi I transpose will come in the beginning and k transpose will be the second term, and phi j transpose will move at the end. Similar on the right hand side also. So what we get is phi I transpose k transpose phi j equal to omega I square, as it is, since it is a scalar quantity. Now phi I transpose come here, m transpose, and then phi j transpose and transpose of phi j transpose, it is becoming phi j. Now we know stiffness matrix and mass matrix are symmetric matrix, therefore their transpose will be the same matrix. So if you see, k transpose is nothing but k and m transpose is nothing but m. If I substitute this back in the expression, what I get is phi I transpose into k phi j equal to omega I square into phi I transpose into m into phi j. Let's rewrite the equation 5. We'll write equation 4 also, which is phi I transpose k phi j equal to omega j square phi I transpose m phi j. Now we'll subtract equation 4 from equation 5. So if I change the signs here, it will become negative, this will also become negative, and the entire left hand side gets cancelled. What we are left with is omega I square minus omega j square into phi I transpose into mass matrix into phi j. Now either of the two terms must be 0, but we know this is subtraction of the two modal frequencies, so they cannot be 0. So whatever is left, that is phi I transpose mass into phi j, this has to be 0. So we can conclude that modal frequencies cannot be 0, therefore phi I transpose m into phi j, this has to be 0. Now let's denote this to be A. Now we can substitute this back in equation number 5. So if I substitute A in equation number 5, the right hand side becomes omega I square into 0, because phi I transpose M into phi j is 0. So we are having phi I transpose K phi j equal to 0. That is indicating mode shapes are orthogonal to each other with respect to mass matrix and stiffness matrix. This orthogonality property is very useful while analyzing multi-degree of freedom systems using modal superposition method.